Alright, what's up guys? In this video, I'm going to pick up with some calculus here. We're going to do another improper integral. So as to just evaluate this improper integral or state that it diverges. So I think this is going to be example number 3 of the improper integrals that I've done. I do have some other examples on YouTube and on my page for you to look at. So maybe this isn't the best one to look at for the first time, but just a general explanation of what an improper integral is. Basically, an integral is improper when either one or both of these limits are infinite. Sometimes one of the limits can be negative infinity as well. Also, an integral can be considered improper even if it has finite limits, but it's discontinuous on the interval of integration. It can also be considered improper in that case as well. So those are a little harder to spot. And you really want to work a few of these because they don't come up all that much. But once you get to Calc 2 and you start learning about the integral test, and if you haven't got to Calc 2 yet, you'll learn about the integral test. And I've also done some videos on that as well. You'll be working with improper integrals a lot. So they don't come up a whole bunch, but when they do, you know, it's best to know how to deal with them. The problem with improper integrals is, as I've mentioned in previous videos, we cannot evaluate them like we would some definite integral with finite limits, because infinity is not a finite value. So we can't just use part 2 of the fundamental theorem of calculus and just plug infinity in there. So what you have to do is you have to replace infinity with a variable, typically t, and then you take the limit as t goes to infinity in this particular case, or as t goes to negative infinity, depending on the situation. So I do have some videos, so check it out. So in this particular circumstance, we have to rewrite this integral, the limit as t goes to infinity. And what we do is we take the variable t and we replace it with where our infinity was. And then you still have your function 3x squared plus 1 all over x cubed plus x dx. Okay, so some improper integrals are relatively easy to evaluate, and you could probably know the, or rather, I shouldn't say relatively easy to evaluate. What I'm trying to say is, if you just think about it being an indefinite integral, forgetting about the fact that it's improper, you may easily be able to tell what the answer is just by looking at it. Like, for example, if I have something like, I don't know, let's say I have the antiderivative of e to the 2x dx. Well, that's just 1/2 e to the 2x plus c. So if that's the case, and you can easily compute the antiderivative, then all you have to do is substitute in the limits from 1 to t or whatever it is, and then take the limit as t goes to infinity. If it's not an integral that you can easily compute by just looking at it, the best thing to do is to compute the indefinite integral first and then substitute in the limits and take the limit as t goes to infinity. So I know that this is just going to give me the natural logarithm, but if you, or it's going to be, our answer is going to contain natural logarithm. But if you don't know how to integrate this, I'm actually going to show you exactly how to do it. And it's just a simple u substitution, but I'm going to compute it as an indefinite integral first, and then we'll do everything else. So it's going to be 3x squared plus 1 all over x cubed plus x. So let's compute the antiderivative first, just as an indefinite integral. And you can do this and then plug in the limits if you need to. So clearly here, this is just a u substitution. Why? Because notice if we pick u to be the denominator here, our derivative is in the numerator. So anytime you see the derivative in there, a u substitution would do the job. So we'll pick u to be x cubed plus x. And notice that if we take the derivative of this, we get what's in the numerator. We'll get 3x squared plus 1. So what that means is we will be able to cancel out the 3x squared plus 1, and then we'll be left to integrate du over u, basically. So this is what happens, just in case you're not sure. So we get 3x squared plus 1. Remember, this became u, and then we multiply it. If we solve for the dx part, we get 1 over 3x squared plus 1 du is equal to dx. So what happens is, or actually you could, if you want to, you could just write it as du over 3x squared plus 1. And as you can see here, the 3x squared plus 1 will cancel out, leaving us with the integral du over u, which we know is ln, absolute value of u plus c. Now remember that u was x cubed plus x. So all we gotta do is put that back in there. So we would get ln absolute value x cubed plus x plus c. That's what the antiderivative would be if it were just an indefinite integral. But it's obviously not an indefinite, it's an improper integral, so you can negate the c in this particular circumstance, but I was just showing you that you can compute this indefinitely first if you need to. But sometimes you won't need to do all that. And if you're good with just recognizing basic antiderivatives, you might not have to do any work at all except plug in the limits and take the limit as t goes to infinity. Some improper integrals are just that easy to look at. And what we're looking for to determine whether or not an improper integral converges is basically the same thing we talk about with the limits. I mean, if the limit exists, it obviously converges. If we get infinity, then it diverges. So that's pretty much the goal. So now that we got the antiderivative out of the way, this becomes the limit as t goes to positive infinity. And it's going to be ln absolute value of x cubed plus x. And perhaps I shouldn't have, well, I'll do it like this. Okay. All right, so apply the fundamental theorem of calculus. And again, we can do it now because we can substitute a variable in there. We just can't plug infinity in. So here's what you get. You get the limit as t goes to infinity. And you just do it the way you would any other definite integral. The t is going to be, or the x is going to be replaced with a t. So that'll be t cubed plus t, the absolute value of all that. And then you'll subtract that from ln of what you get when you plug the 1 in. So that'll be 1 cubed plus 1. And you simplify it down a little bit. All right, so what's the limit here? So it looks like we'll have the limit as t goes to infinity. And it looks like we'll have ln t cubed plus t minus, we can actually drop the absolute value bars for that part. And so your question is, well, what do we get? Okay. Well, this should just give us infinity minus ln of 2. And that's obviously infinity. So since we get infinity after we take the limit as t goes to infinity, then this integral diverges. So final answer, you could say the improper integral diverges. Okay, so as you can see, if you're not familiar with working with these types of integrals, then you might not know how to kind of deal with them if you haven't seen them before. So I highly recommend working on a few examples, because again, this type of integral, improper integral, will jump out at you when you least expect it. It's kind of like what I talked about in the videos where I try to include us taking derivatives and antiderivatives of hyperbolic functions, because we're all aware of what our basic 6 trigonometric functions are, but then you get situations where the hyperbolic ones come out of nowhere, and you're just like, oh my god, I don't even know how to deal with most of these. And the trig functions and hyperbolic functions do have a few similarities, but there are obviously some differences. So it's always good to make sure that you work with some of the topics in calculus that that way that you don't forget how to deal with them. Okay, so that's going to be it. Please check out my other videos for more examples. But I'll see you next time.